Okay, welcome to Mechanical Engineering Systems. I hope everyone is app you are using. Oh yeah, John Duncan. Yes, I am hoping. But I would be honest with you. I don't think many professors use the Zoom the way I use it. Like Zoom is overloaded with there is a PowerPoint streaming, there is an online discussion, writing, recording. So sometimes Zoom crashes. So if Zoom does not crash, then yes, I will upload all the notes. But if it crashes, I won't be able to upload those. But I'll make an effort to save and upload the notes. Okay. So today we are gonna look at design of knuckle joint. Now, how does a knuckle joint look like? So what you have so it's sort of a hinge. So if you look at knuckle joint, this is how a knuckle joint would look. So what you have is, this is called as the eye end. This is called as the fork end. And through the eye end and the fork end, what you have is, you have a pin that goes through. And this pin has a collar. This pin has a top collar. And then there is a lock pin. So I want you to understand this knuckle joint is just like a knuckle joint like this. So you have a central pin, you have an eye end, you have a fork end. So what we want to do is we want to design the important dimensions of this knuckle joint. And just like in last class, I'm gonna give you a step-by-step recipe to design the knuckle joint. Let me identify some important dimensions. This dimension is D. This dimension is D1. Same dimension will be on the eye end. Same dimension will be on the fork end. And if you look at it would be something like this. So it's going to be like this. So how do you design the knuckle joint? So I'm gonna give you the step-by-step recipe. Step, dimension, design concept, resisting area, and remark. So step 1, we have to find out the rod dia. The dimension is D. The design concept is direct tension. So if you think about this area, the area supporting the load P, this is the load P. It's pi by 4 T square. So sigma T is equal to P divided by pi by 4 T square. So for knuckle joint, they will give you the value of load, usually given in kilonewtons. They will give you value of sigma T, which is the tensile stress. They will give you value of sigma C, which is compressive stress. And shear stress. So first and foremost, we are gonna look at the rod diameter, which is capital D. So if you think about this failure, you are gonna have the resisting area, which is circle. Now, second, this is the pin. So I'm gonna show you, this is the pin. So pin diameter, this is small d. Now I want you to understand this pin is in double shear. So you have fork end on one side, eye end on other side. So if this pin has to fail, this pin is going to fail something like this. So there are two areas. So design concept is double shear. The resisting area is 2 times pi by 4 d square. It's a circular cross section. So tau is equal to P divided by 2 times pi by 4 d square. Now, one thing that is many a times for uniformity, this pin diameter is taken same as rod diameter. There are two reasons for it. First and foremost, that when we are trying to design, we want to sort of standardize the design in terms of some principal dimension. And rod diameter, capital D, it's considered as the principal dimension. Second thing, please note that this pin is failing in double shear. It's failing in shear, but when it is shearing off, there are two areas that are resisting the shear. But I want you to think about one other failure mode, wherein you have the pin that is being pulled on the fork end and the eye end. So pin is going to bend. So what would happen is there is a possibility that this pin could bend. And this bending is more severe failure mode than the shear, because in shear you have two resisting areas. In bending, you have this bending moment that is acting at the center span. So what we do is modify pin diameter, modify pin dia for bending. And what that means is D is approximated to capital D. This is just a normal practice for standardization. For standardization. Next step, step number 3, is we have to find out the eye end diameter. So this is the eye end diameter. So eye end dia. And I want you to remember this rule of thumb. Whenever you have a hole and whenever you have a boss, what that means is you have a sort of a washer. So for example, you have a hole with inner diameter and you have a washer. Typically, the outside diameter would be 2 times the inner diameter. So if this inner diameter is small d, typically the outside diameter would be 2d. And this is because you don't want that material to be weak. You don't want, when you are going to drill the inner hole, you don't want any cracks to propagate, or you don't want to provide any chance for crack initiation. So that's why it's a standard practice. If you have an inner hole and outer boss, the outer radius or outer diameter would be 2 times the inner diameter. So eye end diameter is usually 2 times. So D1 is equal to 2 times D. Step 3 or step 4. Step 4. Now we have to find out eye end thickness. So what do I mean by eye end thickness? So if you think about this eye end, I want to find out this eye end thickness. And the way of this failure is possible is a pure tensile failure. So what you have is, you have the outside diameter, capital D1. You have the inside diameter, capital D, multiplied by T is the resisting area, and that is supporting pure tension. So I'm going to call this T, tensile failure, and area is going to be D1 minus dt, and sigma T is equal to P divided by T1 minus T times T. Please note, capital D1 is known, small d is known, capital D1 is known, D is known, so we can find out the value of the thickness. Capital D is now the same as the pin diameter because we modified the pin diameter over here. Yeah. So 5 is, there is another way this eye end can fail. So eye end can fail in shear failure. So how would this shear failure happen? So let me show you. So this can happen like this. And you have this guy. So this just small side can come out. And if you look at this, this is thickness T, and this dimension is capital D1 minus D divided by 2. Everyone understood this? So the small piece in front of the eye actually comes out. It is, the failure is different than the tensile failure. In tensile failure, please understand, the failure is happening over here. In shear failure, the failure is happening over here. So these are the two differences, main important differences in the failure. So what we need to do is, we already have the dimensions, so we have to check for shear failure. So checking. And the area is D1 minus D divided by 2 multiplied by T. But please note that there are two areas. One area this side, and there is another area on the back side. So this needs to be multiplied by 2. So you have to find out tau P D1 minus D T. Now at this point, I just want to mention something very interesting. If you look at the equation for shear failure, and if you look at the equation for tensile failure, even though the resisting areas are different, the equation is the same. Now, what does that mean? It means that if you are going to find, and actually once you work out the problem, you'll realize, once typically the tensile stress of the material is greater than the shear stress. Typically, the tensile stress of the material is greater than the shear stress, which means at this point, if you use step number 4 and you find out value of T, do you agree with me that value of T would be smaller if you were to use step number 5 and find out the value of T? Do you agree with me? In other words, if you look at the equations, step number 4, step number 5, the right hand side is the same, but the left hand side is different. In step number 4, we have tensile stress. In step number 5, we have shear stress. Since shear stress is lower than the tensile stress, the thickness that you find from step number 5 would be greater than step number 4. So in that case, what you will do is, you will select the higher value. So you can find the I end thickness based on tensile failure. You will notice that in shear failure, that joint fails. So you would modify that thickness so that the joint is safe in shear failure and tensile failure. Next thing, check pin for bearing. Now, we discussed this in last class, but I will repeat here. So we have this pin. On one side, this pin has this forked end. And here we have this I end. And if you look at the I end, this is the area that is resisting the load. And on either side, there is load P. Here there is load P. So what we need to do is, we need to find out the bearing stress. So check sigma B. How would you find out sigma B? Sigma B is the projected area. This is small d, which is equal to capital D, and this dimension is T. So the resisting area is capital D multiplied by T, and sigma B is equal to P divided by D times T. And this should be less than sigma B design. So this is something that you want to check. Now, at this point, I want you to understand that we have designed the I end completely. So the major dimensions for the I end are completely known. If you look at the fork end is nothing but the duplicate of I end. So whatever we have on the left-hand side, something similar that we have on the right-hand side. So if you were to use the design calculations or design equations, they are going to be exactly the same. So it's like you take the I end, slice it, and make it into a fork end. And the design equations are going to be the same. But sometimes, just from assembly point of view, or just from empirical testing point of view, we always slightly oversize the fork end. And these are empirical relations. So it's, even though the design calculation would show that, hey, 10 millimeter of I end and 5 millimeter of fork end would be good. But usually we slightly oversize the fork end so that that joint is proportionate, and this joint can withstand not only the stresses but also the deformations and able to sustain its operating all the operating loads. So for the fork end, so fork end thickness which is called as T1, fork end thickness is called as T1, and that is usually the value of P, which is the I end thickness by 2 plus 5 millimeter clearance. So this is sort of an empirical dimension. Then what we do is it fork end and shear failure. This is again to check, and we use the dimension 2 times T1 minus small d, and please note here there will be T1. So this dimension T1 will go over here. So what you will do is you will find tau is equal to P divided by 2 D1 minus D T1. And you can also check shear failure. We did the bearing of pin in fork end, and that again, this is for checking. The resisting area is going to be T1 times 2 times D, and sigma B is going to be P divided by T1 times 2 times T. And once this is done, you can actually complete the design. So I will go through the design process quickly. Design of knuckle joint. It's a very straightforward step-by-step recipe. And understand the fork end is sort of duplication of the eye end, where you take the eye end, slice it into two, and you have the fork end. So first step is design the rod diameter, which is based on the direct tension. Then we design the pin diameter. Pin is usually designed using double shear, but you'll observe that just to make pin safer for bending, what you can do is you can actually use small capital D is equal to small d. I mean, oversize it. Then you have to go for eye end diameter, where outside diameter of the eye end is twice the inside diameter of the hole. Then you find the eye end thickness. Then you check for eye end shear failure. Then you check the pin for bearing, and then check the fork end thickness, fork end shear failure, and then finally you do the bearing of the pin in the fork end. Now here is something else that I want to discuss in a little bit more detail. So this is bending of pin. Now in the last class, I talked about checking cotter for bending. If you look at the way the cotter is held in place, exactly the same way the pin is held in place. So instead of in the last class, when we designed cotter joint, we had a rectangular cotter that we checked for bending. In this problem, in the knuckle joint, instead of a rectangular cotter, we have a circular pin. However, if you look at the loading pattern, and I will show it to you again, if you look at the way this joint is loaded, so you have the pin over here. This pin, on one side, we have this eye end. And on other side, we have this forked end. So if you look at the loading, this loading has the similar pattern as the cotter joint loading. So what it means is you have uniformly distributed load at the center. You have the uniformly distributed load at the center, and you have uniformly varying load at the other side. So if I were to draw the free body diagram, I'm gonna get loading something like this. Do you agree with me that this loading pattern is same as the cotter joint loading? Are you with me so far? So what it means is, please note that this dimension is known. What is this dimension? This dimension is, this is T. This dimension is T1. This dimension is T1. Do you agree with me? That means this total length is going to be T, T1, T1. Just like the cotter joint, you're gonna have a load P, and you're gonna have load P by 2 and load P by 2 over here. So with this load distribution and with this dimensions, can you find out the maximum bending moment which is at the center span? Bm max. And one student asked me this question via email, that how did you derive the bending moment equation? So the way I derived the bending moment equation is I looked at the section and the center span. So this is section XX. And I summed the moment of the forces from the left-hand side of the section. On the left-hand side, I have a triangular load. Then I have a small rectangular load. So did you understand the way I derived bending moment in last class? But because there was one question, so let me just derive this here. So if I were to look at the bending moment, it's going to be something like this. This is my section XX. This is my section XX. You agree with me? This is my load P by 2. Why P by 2? Because there is P coming on the right hand side. That load P has 2 forks. So basically each fork is supporting P by 2. This load is P by 2 because half of the load. So here there is P, but now I'm considering the half of the section. So there is just half of the load P by 2. Now let's look at these dimensions. This dimension is T1. This dimension is T by 2. You agree with me? Now, triangular load, the total load would be at the centroid of the triangle. So centroid of the triangle is going to be at distance 2/3 T1. So what would be the bending moment? The bending moment is going to be P by 2, this P by 2, multiplied by this distance. And how much is this distance? This is T1 plus T by 2 minus 2 by 3 T1, or 1/3 T1 plus T by 2. That is what this is. This force is going down, so I have the negative plus I have P by 2 multiplied by T by 2 by 1/2. This is the bending moment. Now, tau, sigma is equal to m divided by I multiplied by y. Now, please note, we already know the pin diameter. So pin diameter, pin dia is equal to capital D. What is the value of I? So m comes from here. I is pi by 64 d to the power 4, y is d by 2. And this should be less than equal to sigma theta. Everyone understood this? This would be the last step in your knuckle joint design. Any questions, concerns, ideas? Do you want me to work out a problem, or do you want me to just we can do turnbuckle design? Yeah.
So there's like the top part of the program and there's like the side part of it. Side. How do you know?
This side.
Yeah, like the whole side part connecting them.
So those come, these dimensions are non-engineering dimensions, which means these are not the load-bearing dimensions, but these dimensions are important when you are actually trying to manufacture the knuckle joint. So those dimensions come from proportions. Now, how do these proportions come in the picture? So the design that we are doing here is purely based on the principles of mechanics of material. But please understand, the analysis what is done over here is a planar analysis. But knuckle joint is not a planar geometry. It's a three-dimensional geometry, which means it has curves in all 3 dimensions. So the loading is going to be complex. So based on experimentation and experience and empirical dimensions, they came up with some proportions where the knuckle joint can be easily manufactured. Usually the joint would be manufactured by casting, and then the joint can be machined. After casting, you machine the joint, you machine the important dimensions, and then use that. So basically, we would use the empirical dimensions to decide those. For example, you want to have certain radius. You don't want to have some stress concentration. So what would be that radius? So if you look at the textbook, it will give you those dimensions for the radius in terms of the principal dimension, which is d. However, let me tell you, once the basic dimensions are done, the engineering dimensions are done, what you want to do is you want to construct a CAD model and perform the finite element analysis to make sure that the joint that you have designed can withstand the three-dimensional complex states of stress. Because please understand, even though you are just pulling, because of the geometry, you are going to have shear stresses, you are going to have normal stresses. When these two stresses act together, you are going to have principal stresses. So the analysis that what we are doing, we are not doing principal stress analysis, even not in 3 dimension. We can't do that by hand. So that's why in my homeworks, I asked you to perform the finite element analysis that will show you that if you look at the pin, the average stress in the pin would be same as what you calculated. But the stresses where the load is applied would be significantly higher than the higher stresses. That is called as the Saint-Venant's principle. So did you study that in mechanics of material? Okay. So what happens is, so think about a simple tensile loading. Okay. Think about the simple tensile loading. All the analysis that we are doing assumes that we are far, far away from the point of application of load, which means our cross-section area is this. But you will realize when you do the finite element analysis, the stress here is significantly greater than the stress which is averaged out at the center. Because what happens is the stress lines, they kind of go like this. So stress lines kind of go like this. And this is called as Saint-Venant's principle. So in mechanics of material calculations, we are just looking at the average stresses, and we are not considering the stresses under the direct action of load. But when you do the finite element analysis, depending upon the element size you choose, depending upon the resolution that you choose, depending upon the algorithm that you choose, you will get a better representation of the stresses. And that's why when you do the finite element analysis, you will realize that even though you don't expect, there will be some stress concentration over here. There will be some stress concentration over here. There will be some stress concentration over here, stress concentration over here. So I have asked you to do the finite element not only on component level, but on the assembly level. So we are not studying the stress analysis at assembly level. We can't do it. So for that, you have to use the computer software. So once you do it, you will realize that basically at the contact points, the stresses are significantly higher. And those contact stresses are called Hertzian stresses. So, and what happens is, because of those extremely high localized stresses, there is pitting. The material gets removed, a teeny tiny amount. So what we do, that is the reason why you would notice the pin and the inner surfaces, they have surface finish requirement. Why surface finish requirement? Because the amount of pitting will be reduced if you have a smooth surface. Rather than having a rough surface, then that will give rise to more localized stresses. If the surface is smooth, then basically the localized stresses would be minimized. And that type of analysis, you can do that using finite element analysis. That is not possible to do with hand calculations or mechanics of material concepts that we study. So when you go to industry, you will actually determine some basic dimensions, and then you will directly move on to CAD. And all your analysis will be done using SolidWorks, CATIA, Creo, or Autodesk Inventor, or some other software. So that is how the design is done. Okay. Any questions? So if you have any questions related to design, please ask away. And there are tricks that you can do. So for an example, so let me ask you this. As a designer, I tell you that, hey, I have this knuckle joint, but I want to minimize, here's the question, I want to minimize the contact stresses. What would you do? You can't increase the gap because otherwise the joint would be wobbly. And actually that's dangerous. Why it's dangerous? Because you would have impact loading when the load is transferred, and that is significant. But what I can do is I can add a sleeve. What I can do is I can add a deformable sleeve somewhere here. And what would be the purpose of this deformable sleeve? So and this is what you will see if you look at the vehicle chassis, look at the bearing, that is where the bushing goes inside. You would add some sort of a liner, some sort of a bush. And the purpose of that bush would be just to deform. It could be something like a brass. The only function of it is deform and make that surface smooth. So that would minimize the contact stresses, and that would actually increase the longevity of the joint. So there are small tricks that you can play. And once you look at different mechanical components, even simple machine components or design, when you look at your automotive or car or bearings, bushings, you will see that there are these small design principles that are used to make sure that that joint or that particular design is safe. So just keep an eye open and then think about the design principles, how those design principles are used in actual practice.
If they design the sleeve, do they make it like the same length as the rod, or are they like for example, do they put them, attach them to the fork and eye ends? Or
so here is what, if I were to add a sleeve, what I would do is I would add a brass sleeve over here. It would be pressed in to the eye and the fork. So that is how I would do it. Any other questions? Questions from my online students? Okay. Now I'm gonna talk about design of turnbuckles. Now, have you seen a turnbuckle? So a turnbuckle is something like this. So you have clockwise threads on one side, and you have counterclockwise threads on the other side. And then you have screws over here, and you have screws over here. So now here is what happens. If you rotate the turnbuckle in one direction, both the ends, so for example, this rod and this rod, they come together, they come closer. If you rotate the turnbuckle in the opposite direction, they go away. Now, what are the applications of turnbuckle? Turnbuckles are used as tensioners or support members. And when you drive around 202 or maybe Power Road, you will see these lamps or lamp post. And you will notice that there is actually a turnbuckle somewhere over here. That is used to adjust the tension in the cable. So have you seen the turnbuckles? You rotate turnbuckle in one direction, then basically you can actually, it comes together. Similar concept. I don't know if you work on cars. If you have slightly older cars, then that don't have hydraulic tensioner, they usually have some sort of turnbuckle type tensioner, wherein what you can do is basically the idler pulley gets moved top or bottom depending upon in what direction you rotate. So basically you can have a turnbuckle that will adjust the center. So now there is a difference between the turnbuckle and the power screw. So again, this is a screw and this is the nut. Again, this is the screw and this is the nut. So what is the difference between the turnbuckle and the power screw? In power screw, you are going to use the nut and the screw to transmit power. What does it mean? I want you to think about the 3D printers that you have. You have a lead screw and that lead screw rotates and basically the slide can go up or down or forward or backward. So what is happening? The rotation of the screw is causing that nut to go up or down. This is important. Rotation of the screw is causing that nut to go forward and backward. That motion is continuous, so the power is continuously transmitted. But turnbuckle is static. Turnbuckle is not used for power transmission. Turnbuckle is sort of an adjustment or adjustable joint. So basically you rotate the turnbuckle, adjust the tension, and that's gonna stay there. Then you are not going to touch the turnbuckle. This is the basic difference in the turnbuckle design, even though it's a screw, but it's not a power screw because it is not transmitting power. It's stationary, it's not moving. On the other hand, lead screw, or if you look at the lathe or any other power transmission mechanism that uses the lead screw and nut, that is continuously moving. So turnbuckle is used for static applications and power screw is used in dynamic applications. And I will give you the design process for the turnbuckle, and then we will discuss in the next class, we'll discuss the design of springs and design of power screws, and we will do the design of screw jack. So how would you design the turnbuckle? So whenever you design a screw, let's talk about how the screw gets assembled to a nut. So this is the screw. And then here there is nut. It could be clockwise, it could be counterclockwise, doesn't matter. But I want you to understand that this is how the assembly is going to take place. So what type of failures you would expect in a screw joint? So in the screw joint, you have an outside diameter and you have an inside diameter. And imagine that you apply the tensile load. What would happen is the inside diameter it's a circular cross section, it could fail in pure tension. So there is a tensile failure. The next thing that is possible is these threads can come out. So basically, I don't know if you have seen a stripped screw. When what happens is basically the screw has some threads, and then basically all the threads are stripped. Then you will see those threads coming out. So there were threads here, but they got stripped. Then this is the bolt. So something like that. So basically, you can actually have the threads failing in shear. The threads, depending upon, I want you to understand that here you have 1, 2, 3, and 4. You have 4 threads in contact. So if you think about it, they could crush, which means if you apply the load, think about applying compressive load instead of tensile load. Now you are applying compressive load. And what would happen is these threads, they crush. So there is a crushing failure that is possible. So we are going to design the turnbuckle based on these static failure modes. When we design the power screw, we will look at the friction, frictional torque, and all that stuff. But here, we are going to design the turnbuckle based on the static failure. So, how do we design? Design procedure. First, core dia. That dimension is DC. That is using direct tension. And that cross-section resisting area is pi by 4 DC square. So equation is sigma T is equal to P divided by pi by 4 DC square. And from here, you can find out value of DC. So in turnbuckle design, they will give you the value of P. P is known. Sigma T will be given. Sigma C will be given. Tau will be given. So first and foremost, we have to find out the core diameter that is using the direct tension. That is a step 1. Step 2, we have to find out the nominal diameter or outside diameter, which is D. This is an empirical dimension, and which is D is equal to DC divided by 0.8. And sometimes you can modify this nominal diameter, modify based on standards. Because please understand, nobody is going to make custom screws for us. So if we find out our core diameter is 8 millimeter, nominal diameter is 11.2 millimeter. If you go to McMaster Car, or if you go to Amazon, if you go to eBay, or if you go to some other vendor like Granger, nobody is going to give you 11.8 millimeter screw. What you will do is you will see what screw is available. You say 12 millimeter screw is available. That's good for us. 12 millimeter outside diameter, 8.5 inside diameter. That's totally fine. So you modify these dimension based on the components that are readily available. Then next step, length of the nut. That is empirical dimension, which is B is equal to 1.25 times D, and this D is this guy. Then step 4, check threads. For shear. And if you look at the shear area, this is exactly same as the circumferential shear, which is, you will say pi. So this is shear pi times d times b. So tau is equal to p divided by pi times d times b. Pi times d times b. Next step, check threads for crushing. And this is, so crushing compression. The area is pi by 4 d square minus dc square. So sigma c is equal to p divided by pi by 4 d square minus dc square. 6 nut diameter. It is from direct tension. And which is pi by 4 capital D square minus small d square. And outside diameter, again this is direct tension. Which is pi by 4. This is d2 square minus d1 square. Sigma t is equal to p divided by this area. Sigma t is equal to p divided by this area. And let me show you the a nice sketch that kind of will give you all these dimensions. So you have screw over here. You're gonna have clockwise on one side. You're gonna have counterclockwise screw on the other side. And then here, you're gonna have this nut. And the dimensions are, this is DC, this is D, this is L, this is B, this is D1, and this dimension is D2. And this L is typically 6 times D. So this is how you will design a turnbuckle. Step 1 in designing the turnbuckle, they will give you the load that needs to be supported, the values of sigma t, values of sigma c, and value of tau. And then first step is to find out the core diameter from direct tension. Then we have to find out the nominal diameter, modify that nominal diameter based on the standards. Then come up with the length of the nut, which is B is equal to 1.25 times D. And then check the threads for shear, check the threads for crushing, then check the nut diameter or find the nut diameter for direct tension. This is D1. And then find the nut diameter on D2. So that is how you will design the turnbuckle. But please understand, for turnbuckle to be operational, minimum 3 threads should be in complete engagement. If you have just one thread, you may think that, hey, turnbuckle is functioning, but it's not strong. So you must have minimum 3 complete threads, not the threads at the entry or threads at the exit. So for an example, threads here and threads here, they are not load bearing, they are just guiding, because these threads are not complete, they are incomplete, they just guide the screw. So you should have at least 1, 2, 3, 3 threads in complete engagement so that the joint can stay safe. Everyone understood this? So this turnbuckle is slightly different design and there are variations to it. So for an example, if you were to look at, and I'm sure you might have seen the turnbuckle like this. This turnbuckle design is something like this. So it's like a big nut. This is the design. This is how that turnbuckle, and the turnbuckle that I have shown over here, this is a slight variation in the design. The principle is the same. The only thing is, if you want to design this type of a turnbuckle, you would consider this cross section and see the failure in tension, and then you will decide what would be the dimension of the center cross section. But there are variations. So for an example, this turnbuckle is used for simple applications when the loading is not high, and you can actually use a wrench and tighten the turnbuckle. But if you need to support high loads, then perhaps you need to insert a bar through these two and rotate the turnbuckle. So for if you look at the turnbuckles that are used near the power lines, they would be something like these. If you use the turnbuckles that are used for screws and compass or for fine adjustments, they would be something like this. So there would be knurling, and then you can rotate, and then you can adjust the turnbuckle. Okay, any questions so far? Capital D is D1. Oh, okay, hold on. Yeah, capital D is D1. This, oh, sorry, this guy. Oh, yeah. So, okay, I made a mistake here. Oh, this is D. So, this not D. This is D. Sorry. This is D, which is DC divided by 0.8. Yeah, you can add the names. You can add 3D printed names, or you can add markers. That's totally fine. So it doesn't matter. Okay, any questions? So I think you guys should be good for homework 2 as well, right? Turnbuckle is homework 2, right? Homework 3? Okay, so let just tell me quickly what is.
There's the double quarter joint, the turnbuckle, and then the joint.
Oh, double quarter joint. Everyone comfortable with double quarter joint? Have you tried? There is a very nice worked out example in the textbook on the double quarter joint. Exact same principle. Take the quarter joint and design. What we have designed is half of the quarter joint. So what you have in double quarter joint is basically you have something like you have 1 quarter over here, 1 quarter over here, and then the rod over here. The principle is the same. You don't have to repeat the process. Just actually design the half of the quarter joint and that exactly is duplicated on the right hand side. There is a worked out problem in the textbook on double quarter joint. Please take a look at that. I also have a worked out problem. If you still have questions, or if you struggle, I would be happy to work out a double quarter joint problem in class. So any other questions? Okay, then I'm going to stop here, and I would be happy to answer any questions you may have.
Hi,